So, we sort of did a little more a method of characteristics, right. So, we derived some equations, got some expressions to play with. Let us sort of go back and revive that a little bit. Let us do the discussion that we kind of left out yesterday, right. So, okay, let us say, so we took the governing equation for say 2D irrotational flow, right, for the 2D irrotational flow, and we got something like, we said we could write it like this, right. And we said we could solve this on a computational grid, right. That is the basically the beginning of computational fluid dynamics, and we could solve this on a grid, knowing the derivatives at say location. So, this is say at a particular location in the flow field. Okay. Having divided that domain, having divided the consider a domain in that flow field, which we are discretizing in a certain way. However, there is a catch that this will exist only as long as this is not 0. Okay. So, when this becomes indeterminate, when this becomes 0, then del u del x becomes indeterminate, right. So, what we saw is that, which means that u is equal to a. Right. So, if in my computational grid, so therefore, if at a particular, so if I say have a grid, or say at any point in my flow field, so somewhere at my flow field over here, right. So, this is the streamline direction, this is the velocity vector, right. Then it so happens that this is the u component and this is the vertical component of this, and it so happens that this u is equal to the speed of sound, u becomes sonic. So, therefore, then if we have a line, right, this line is part of the grid, right. So, if we have this line, right, which is making an angle mu with the streamline direction, right. So, this is a line which makes an angle mu with the streamline direction, right, and the velocity component perpendicular to this line is sonic, right. In that case, we were able to see that the derivatives, the derivatives of u and other properties will become indeterminate and also become discontinuous, may become discontinuous on this particular line. Right, and such lines are basically the characteristic lines. Okay. So, if I may do that repetition one more time, and if you can, so basically this is a line, right, which is making an angle mu with the streamline direction, with the velocity vector at say this particular point, which is a. Right. And this is basically any arbitrary point in the flow field, and the velocity component perpendicular to this line is sonic. Right. Then the derivatives of the velocity component here u is going to be indeterminate and may be discontinuous on this line, and therefore, this line is essentially a characteristic line. And what we can also see from here is that, if you see from here, right, this is mu. So, sin mu is 1 by m, which essentially means that these are also Mach lines. These are also Mach lines, right. Now, we then went on to, so this is something we did, and then we went on to we worked with this, we found out an expression to find out, say, velocity potential using the velocity potential equation, and we found out to be, okay, say some numerator by denominator. Okay. Now, here too we have to come up with a similar kind of analysis like we did here. Now, this phi x y, right, the phi x y becomes indeterminate, okay, if d is equal to 0. Okay. Now, basically now phi x y will always exist only if d is not equal to 0. But say we put d is equal to 0, then phi x y becomes indeterminate. And what we have seen over here is that the derivatives, okay, become indeterminate on these lines, which are characteristic lines. So, therefore, here if we force this d to be 0, okay, so then the derivatives will basically, so for these derivatives to become indeterminate, we can set d to be 0. Right. Now, d is 0 means what we get from here is that the way we choose our dx and dy. Okay, let me sort of write this out. This will make a little more sense then. Okay. Okay, so this is okay. So, okay. So, as you can see here, so therefore, if I choose dx and dy in such a way, so in a particular flow field, so this is say for some streamline like that, right. So, if I have say a particular at say this particular point, say, right, this particular point, this is my streamline direction, this is my v, right. Now, I choose a dx dy here. So, I choose a dx and a dy, I choose a dx and dy in such a way, right, that this d goes to 0, that d goes to 0. Then the derivatives, okay, of the derivatives of my flow field are going to disappear, are going to become indeterminate and may also be discontinuous. Okay. Now, let us look at this. Now, for example, let us see. Sorry, let us say this is this velocity u. Okay. Now, say this is varying something like this. Say this is following. So, I have just taken an arbitrary fashion something. So, let us say okay. So, let us say this point is A and this point is B. Now, if you see from here, so del u del x is 0, right, on the x axis. Right, on the x axis, this is also parallel to the x axis. So, del u del x is 0 over there as well. Okay. And somewhere anywhere on this curve at some point, okay. So, you can see here. So, somewhere, so del u del x is some sort of a constant. Okay. So, it will vary in this direction. Okay. Now, if we have something like this, so say this is at the most it can be a constant. So, in that case basically then we can have say a straight line. So, say something like this. Okay. Now, as you can see, say for example, at this point A and B. Okay. At A and B, the derivative is not uniquely determined, right. So, in here u is continuous, right, here also u is continuous. At points A and B also u is continuous, but del u del x is not independently determined, it is not uniquely determined. So, it is discontinuous at A and B, right. However, right, the value should lie somewhere between this 0 and c, is it? The value should be somewhere between 0 and c. So, therefore, for this to be at least, for my derivatives to be at least finite, it has to be at least a 0, right. It has to be at least a 0, and to enforce that I have to make n is equal to 0. You understand what I am doing here? So, what essentially I am trying to say is that now I am choosing directions, okay. I am choosing directions which here are the characteristic lines on which the derivatives become indeterminate, it may be discontinuous. So, for which I set d is equal to 0. But for these derivatives to be indeterminate, but at least finite, the n also has to be 0, okay, which means that phi x y, okay, which is del u del y is indeterminate. Are indeterminate. Okay. So, therefore, we found out setting d is equal to 0, what this gives us is how the characteristic lines are located with respect to the flow field. Okay. They do not necessarily have to be straight lines like we had done for the grid here. Okay. Now, so what d is equal to 0 does is essentially tells us how these characteristic lines are located, what is their orientation with the local velocity vector. What n does is essentially gives us the relationship of the properties, the way they are related to each other or how they change over these characteristic lines. Okay. So, therefore, now what we also did is that we were able to find, right, the equations of the characteristic lines setting d is equal to 0, right, and we found this out, right. We were able to find dy by dx is equal to right. And this was also, we also said that this is also equal to this, right. So, if we have something like this, so this is dx and dy. So, essentially the orientation of the characteristics is given by that, and say this is u and v. Okay. So, we found out this, and so this was the relationship we got by setting d is equal to 0, right. So, what this is essentially telling us that we get two lines, right, two characteristic lines provided m is greater than 1. So, which is for supersonic case, and what we get here are hyperbolic PDEs. Okay. So, for compressible. So, for our cases, so our study here, what we are going to do is essentially consider the case where we have, right. So, m is greater than 1. So, we have basically two characteristics. So, at a particular point, say at a particular point like we said, so say this is a say this is some sort of a streamline, okay, some sort of a streamline. So, therefore, my velocity vector here is is this. Okay. This is my velocity vector. So, what I have over here, okay, it could be any line, like that. So, let us just say this is C plus, this is a right running characteristic, and we can have another one. Okay. So, this is C minus, and this is making an angle, say mu, and this is making an angle mu. Note the directions by the arrows, right. So, these are basically C plus and C minus. Now, the question to ask here is, are these straight lines? Can these characteristics be straight lines? Okay. Now, just look at this. Now, for example, this is a streamline, right. This is a streamline. Now, for example, at say this particular point. Okay. Now, I have, say, at this particular point, this is the direction of V. So, what we see is the direction of V is changing, right, on this particular streamline. So, the direction of C plus and C minus will also change at this particular point. So, they do not necessarily have to be, so they will be differently oriented at say this particular point. Okay. So, C plus and C minus do not necessarily have to be straight lines. Okay. They can be curved lines, and we will see that. Okay. Now, having done these, okay, that is so much as what we done with this. Now, and we finally came up with the compatibility equations. Okay. What we came up with the compatibility equations by setting n is equal to 0. So, let us see what that looks like, and let us see what we will do with that. Okay. Now, so we set n is equal to 0, and what we found out was that we were able to these are constants. So, this is the Prandtl-Meyer function, okay, and theta is basically the streamline geometry definition here. Okay. So, tan theta is V by u. So, that is what we get by theta. So, now here this is similar to the Riemann invariance that we did previously, and this is valid for the left running characteristic, and this is valid for the right running characteristics. Okay. So, this is what we have found in terms of the compatibility relationships. Now, let us see what what sort of a problem we can solve with this, or what we will do with all this information that we gathered. Okay. Now, let us say we have this sort of a problem to do. Okay. Okay. So, this is the problem that compute the contours of a 2D for the expansion of air to a design exit Mach number. Okay. So, now it seems that we are kind of at the crossroads, right. When we started with this course, we talked about Laval's experiment and how to get supersonic flows. We need convergent divergent nozzles, right, to get flows which are at such high speeds. We need to sort of design the ducts through which it was flowing. So, we seem to come into a point where we are going to try and design such a duct, okay, depending on what sort of Mach number we need at the exit, right. So, depending on how fast we need our flow to be, we want to design the design a duct, well, that is what we are going to do. So, do a converging diverging nozzle, right. So, that is what this is about, but there is something here which I guess I need to explain. What is this 2D minimum length nozzle, right? What does this mean? So, let us see what this means. Okay. Now, for example, what we basically do is that you have flow. This is what we have done, right. This is what we have done. This is basically the converging divergent nozzle. Now, you have basically subsonic flow coming in here. This is the throat region, right. This is the throat region. The flow is allowed to expand, and then basically we should get uniform flow at the exit. Basically, we will get uniform flow at the exit, right. So, now what happens here is that now you allow this thing to expand over a certain length. Okay. So, what we are going to basically have here is that the flow is going to expand. So, in this particular case, okay, so say we are going to have this. So, we are going to have say several. So, this is an expansion fan. Okay. So, I am going to represent this expansion fan like this. Okay. So, what happens is, okay, now it hits the wall over here, okay, hits the wall over there, reflects from there, and when it reaches say this particular point over here, okay. So, this particular point over here. So, I am going to call this say it does not reflect anymore, it stays parallel, and it parallel, and what we get is uniform flow in this region. Okay. Now, similarly, what happens here is that it goes over there, right, and that is it. Okay, it does not reflect anymore. Then we have this. Okay. Does not reflect anymore, right. Now, we can do the same thing over here. So, you have this flow expanding over here. Now, we could have the same flow generating from here as well, right. Let me do it this way. Let me do this by dotted lines. Okay. Now, for example, this, okay. Now, that comes out here. So, this goes then. Okay, does not reflect anymore. So, similarly, we have for this. Okay. And then again we will have say Okay. So, what essentially is happening is that there is a lot of reflection. Okay. So, we have this flow which is sort of expanding in this region, right. It expands in this region. So, the flow which is expanding from here, it gets reflected, it expands from here, gets reflected from this wall, it hits here, and finally, it reaches a section where it does not reflect anymore, and it moves, it just sort of becomes parallel, and we get uniform parallel flow from this duct. So, similarly, you have flow which is expanding from here, it reflects from here, it goes here, reflects from there, and finally, it does not reflect anymore, and it goes past this. Okay. How are we representing this? We are representing this essentially when I have these lines. If you remember the shock tube, right, we represented this as an expansion wave, that the expansion wave, right. That is what we are doing over here as well. These lines essentially mean, so now these are basically characteristic lines or Mach lines, right, with a series of Mach waves traveling. So, now we are doing this. Okay. So, now what so you can see that this will need kind of a long sort of a it will need a long duct. When you allow this to sort of expand over sort of this region, right, and finally you have, and you can see this, you can see the difference in the region. Okay, my artwork is not very good. Okay, it's not at all symmetric. It should be actually, but it's not very symmetric. But I'm trying to get with a point here. Now, you can see that this area out here is all intersection of various characteristics. You have right running characteristics and left running characteristics. So, these are all sort of interacting with each other. So, therefore, these lines, okay, when they interact with each other, now these are going to be curved. Okay, except now once you come to here, so if you come to say this region, you have only say right running characteristics and only one type of characteristic. So, this becomes a simple region, whereas something like this where you have an intermingling of a lot of both types of characteristics, this is a non-simple region, and here the lines are curved. Okay, here however, it becomes straight lines, and beyond this point of course, we have flow which is parallel, and that is at the exit Mach number. Okay. Now, therefore, you have supersonic wind tunnels which are going to be very long when you allow for this gradual expansion. Okay. But if you want to decrease the if you want to decrease the length of it, the size of it, you want to use it in a rocket, okay, a fast moving aircraft, then what do you do? Then what we can do is essentially decrease sort of this expansion region. We want to decrease this expansion region, okay, basically the non-simple region. So, in this non-simple region we can decrease that to a certain point. Okay, so that this becomes not just a spread out expansion fan like that, but a centered expansion fan. It will expand only at a particular point. So, when you have that, then let us see what it looks like. Okay, let us do that. Okay, so let us do this here. So, for example, the thing is, so essentially, okay, now see the artwork is not good because it just becomes straight after a point. Okay, I am sort of curving it in. So, okay, that is it, and let us put a center line here. Okay. Okay. So, if we have this, so now this is the throat region. Okay, this is the throat region. Now, as you can see that we do not have like we have essentially multidimensional flow coming in over here. So, for all practical purposes, this is not going to be a straight line. right, the sonic region, because it is not expected that it becomes sonic exactly along this straight line, it is going to be a curved line. But for our practical purposes, we will just take that as a straight line. So, let us call this as say AB, and this is essentially the sonic throat region. Okay. So, then unlike in this particular case, when we allowed it to expand over a region, we are going to reduce that region. So, if in this particular diagram basically, so AC this length is your expansion length. Okay. And after this it becomes, this is a straightening portion, it straightens out. So, that sort of deals beyond say CD is the simple region. Okay. So, here what we will do is that this is the, we will decrease that L to completely, we will reduce that L to completely 0, the expansion region to completely, we will just get rid of that. Okay. So, that we do not give it any region to expand, it has to expand at a particular point. So, to do that, so let us say we will, so essentially this is the wall, right. So, let us do this. So, let us say write it like this. Okay. So, I have basically expansion fan. Now, what is going to happen here is that this is not going to reflect. Okay. It is, once it reaches this wall here, it will directly just flow out parallel. Okay. That is the difference between the when we reduce the expansion region. So, similarly, okay, so similarly we have okay. Okay, so that's it. Okay, so that's pretty much what you can see. Now, as you can see over here, that this region out here becomes non-simple, isn't it? Now, these are all like interacting with each other. This region becomes non-simple. So, and rest you can consider that as straight lines. Okay. So, therefore, this is what we do when we have a minimum length nozzle. Okay. So, you can see that now we have basically centered expansion wave. It is a centered expansion wave, and the middle portion here, it also likes, it's like a surface or a dividing line, and you can see from here the symmetry of this, right. So, during our calculations, as long as so what we are asked to do here is that if I have a flow, then my exit Mach number here. So, now when the flow comes here, I will get uniform flow like this, right, and this Mach number is 2.4. So, what I need to do now is to design this wall, basically design this wall. So, design this minimum length nozzle, right. So, what we will just sort of do that here. Okay. Now, as you can see, now this one, okay, let us sort of say, so let me define some geometry. So, what we are going to do here is essentially use the symmetry. Okay. So, what we will basically design just the top part of it. So, we are going to not look at this part. Okay. So, let us just say erase that. Let us just say get rid of that. Okay. We are going to deal only with this. Okay. Now, and let us see what happens. So, this is what we have. Okay. So, this is what we have, and let us see how we are going to go ahead and do this. So, let me call this as some number. So, yeah, so M Mach number is, so let me call this as Mach number at the exit, which is ME, right, and here Mach number. So, here actually Mach number is 1, this is the sonic region. So, we have this. Okay. So, okay. So, this is the minimum length nozzle, and then let us call this as say this point is say small a. Okay. So, now if we have this, okay, and let us say call this point as C. Okay. We will call this as C. Okay. Okay, I get rid of that. Okay. So now if we sort of do this over here, so you can see that these are the right running characteristics and these are the left running characteristics, right. Now here design wise, so this is essentially, this is say theta max, and you can clearly see here that here at this point, of course, theta is equal to 0. So that is our geometry. Okay, that is our geometry. Now let us use the compatibility equations. Now what we had was that theta is equal to a constant, right. This is on the left running characteristics, like it is left running characteristics, and theta on the right running characteristics. So based on that, what we can say here is, say along this characteristic. So along this characteristic, okay. So what we will, this is a right running characteristic. So let us write it here. Okay. So say let us see. So on C A. Okay, this is the right running characteristics. So we can write, say at theta c. So theta c do you think that's okay? So essentially what we are looking at is this characteristic. Okay, we are looking at CA, which is a right running characteristic, and therefore we are using the compatibility equation, which is this, right. So therefore theta c minus nu c is equal to theta a minus nu a. Okay. Now here what is theta over here? Theta over here is also 0, right. Theta over here is also 0. So theta a is also 0. Okay. So theta a is 0 and theta c is also 0. So what we get from here is that theta, so that what we get from here is essentially mu a is equal to mu c, right. We get that. Now, right. So we get this, and also now we also know that this mu a, right, this mu a, which is equal to mu c, is also equal to the mu which corresponds to the exit Mach number, isn't it? So therefore this also we can write as, this corresponds to the exit Mach number. Okay. So this is as much as we know from here. Okay. Now let us look at, for example, now let us look at say AC, okay, which is a left running characteristic. Now if I look at AC, okay, so and again apply the compatibility equation here. So what we get is theta a plus nu a, okay, is equal to theta c, right, plus nu c. Okay. So now what we are looking at, you see, when we took CA, okay, when I wrote this equation, I am using this C here, I am also using C here. What I am doing here is that I am considering the right running characteristic, hence we are getting this from there. Okay. And here we are using a left running characteristic between A and C, and therefore this is what we are getting. Now what we did just now is that theta c is 0, right. Theta c is 0 and theta a is of course theta max, right, is theta max. Now theta c, let us sort of look at this over here. Now this mu a, okay, now mu a is essentially for a Mach number which is m is equal to 1, okay. And if you remember, the Prandtl-Meyer equation is right. So, I can write this as theta max is equal to say mu a minus mu a, and this is minus mu 1, right, which is 0, right. So, mu a is also equal to theta max. Okay. So, mu a is also equal to theta max, okay, which means, and now this mu c is of course equal to the polynomial function corresponding to the exit Mach number. So, I can so this again is mu exit Mach number. So, therefore, what we get from here is theta max is equal to of the exit Mach number by 2. Now, this is very interesting. So, now you can see, now if I have to design my, so just let us take a step back and look at this. So, what we have found out here using the compatibility equations, that given the exit Mach number, this is all that we are given, that is all we are given. So, how do we start out to design this nozzle? So, what we found out is that theta max, which is here, right, is equal to half the polynomial function based on the exit Mach number. Okay. Now, so essentially what we are saying here is, now if you have a length, you need a minimum length of this. Okay. So, you can start from theta max and gradually go up and straighten it out, right. So, you need this minimum theta max, and if you decrease the length below this, then it will not be shock free, then you will have shocks. So, to have shock free parallel flow, okay, here based on this Mach number, this is the minimum length you need. Okay. So, this is the length that we shall be needing. So, now let us sort of do this, do this problem, and let us see how we will sort of go about this. It is the same thing. Okay. So, for our specific problem here, okay. So, our specific problem here, okay. So, let me sort of draw this, say one more time. Okay. So, or shall we do it over here? Okay. So, all right, let us sort of do this over here itself, okay, because this is the this is what we are looking at. So, having found this out, how do we go about designing for our particular case? Okay. Now, let us say in this particular case, what I have done is said taken say 7, right, 1, 2, 3, 4, 6, 7, 8 lines. Okay. So, say 1, 2, 3, 4, 5, 6, 7, 8. Okay. So, now we have this, and yeah. So, what is happening here, what I have done here is, you can see I am just representing the expansion wave, I'm now this is a numerical method, right. So, now the more number of characteristics that you take, you will get better estimation of the properties within that region. Okay. So, in this case, so obviously, when you write a computer program, you can actually do it with more accuracy when you have more and more curves. So, I am sort of just giving you an example out here. So, okay. So, similarly, we will have, say this will go out and will go out, and basically how we will go about solving this problem, right. So, we will have things like this. This is my essentially my region, right. So, what we will do here is, So, this is my theta max. So, how do we number this? So, what we are going to do is we are going to number this whole thing. So, we are going to call that as A. Okay. So, we will call this point as 1. So, this you can see here, this is we have actually created a grid. Okay. We have created a grid in a very different way. Our grid looks different because it consists of Mach waves. These are characteristic lines. Okay. So, this is 1, this is 2, this is 3, this is 4, 5, 6, 7, 8, 9. I'm sorry, it looks a little congested, but you know, I'm afraid you really can't do too much about this here. Okay. So now, so this is how I'm numbering it. Okay. So what I do is on each first line from here. So I said 1 and 2, 3, 4. I go along to the wall, right? So again, I come over here, or did I? Okay. So I guess I took one more extra line. Okay, doesn't matter. So I can sort of just to maybe decrease one more. Okay. So if I say do that, it'll give me some more space actually. If I do that, okay. So let's say I decrease. Let's say I decrease that, okay. So therefore, you can really take as many lines as you want, and that's basically going to give us a better estimation of things, okay. Okay, so if you have that, so then this is 6 and this is 7, right? And so this point is 8. Okay. So then we come here, this becomes 9, this is 10, this is 11, this is 12, 13, 14, right? Yeah, so on and so forth. So then you come here, this becomes 16, 17, 18, and so on and so forth, right. So this is what we get now. So and I know my exit Mach number. My exit Mach number is, and that's all I'm given. So my exit Mach number 2.4. So therefore I can find out my theta max, right. So my theta max, right, is corresponding to right, and what I get from here is essentially okay. So what I get from here is this. So having found this out, okay, having found this out, so theta max is essentially 18.375. Okay. Now what we are doing, so essentially this is it. This is my theta max, and you can see that these characteristics, the way I have inclined them. So this is really up to the user as to how that person does that. So now let's say that this angle, let's take that that A1, okay, say that makes an angle 0.375 degrees. So then therefore each of these are then basically that angle is divided into remaining 18 degrees is divided into 6 divisions, right. So therefore, so A1 is this, okay, then say A9, the theta is 0.375 plus yeah. So therefore my delta theta becomes 18 by 6, which is 3 degrees. So it's 3, right. Then A say 16, right, A16, that becomes 0.375 plus 2 into 3, so on and so forth, so on and so forth. Okay. So what we should do here is again use the compatibility equations and properties, and we will complete this problem. Okay. So basically using the and see if how we are going to locate. So what you have to understand here is that we don't have this profile at this point of time. We don't have that, right. All we have is we are asked to design this. So we need to locate where 8, 15, 21 is with respect to A. We don't know that yet. All we know is this. Okay. Based on that, we were able to find theta max. Okay. Now, we have been able to orient these mark lines, okay, which are in the expansion wave. Now, let us see how we will design where these points are located, and only then we will be able to design this point, design this. So, we will complete this in the next lecture. Okay. Thank you.